Our today's topic is relation between direct and reciprocal lattice. In this topic, we discuss firstly what is the difference between direct and reciprocal lattice. Then geometric relationship between direct and reciprocal lattice is shown by animated GIF image. And then we derive the relation between direct and reciprocal lattice vectors. Here we give some distinguishing point between direct and reciprocal lattice. We know every crystal structure is associated with two lattices, that is real lattice or direct lattice and reciprocal lattice. In direct lattice, the lattice is the geometrical pattern of the crystal where all atom sites are represented by geometric points. If all points are equivalent, that we call the Bravais lattice. Non-Bravais lattice points are not equivalent, as well as the separation between the 2 points or the atoms is same throughout the structure, and it is of the order of few angstrom. Such a geometry of set of the points is represented in a real lattice, or it is the lattice in ordinary space or real space. On the other hand, in the reciprocal lattice, it is the lattice in K-space or Fourier space. Second point is that the primitive vectors have dimension of length. If we join point to point by the translation vectors along x and y axis, these are the primitive vectors and have dimension of length. On the other hand, reciprocal vectors have dimension of per length. Next point is that microscopic structure is a map of direct lattice of a crystal. Since all atomic arrangement in a direct lattice, which having very small separation between the points of the atoms, and it is of the order of few angstrom. Therefore, it is a microscopic structure. That structure is a map of direct lattice of the crystal. In reciprocal lattice, any diffraction pattern of a crystal is a map of reciprocal lattice of a crystal. That we discuss in the next point. In direct lattice, we get the periodicity of the medium. In the reciprocal lattice, it refers to frequency of waves that can propagate in the medium. Here the smallest unit of volume V, that smallest unit represent a primitive unit cell, and such a cell, unit cell in the direct lattice is known as the Bravais lattice. It is Bravais lattice since environment about each and every point is same throughout the structure. Therefore, it is a Bravais lattice of the direct lattice. In the reciprocal lattice, the primitive unit cell is known as brilliant zone or Wigner-Seize cell. How to construct the Wigner-Seize cell in the reciprocal lattice? Firstly, draw lines to connect a given lattice point to all nearby lattice points, and at the midpoint and normal to these planes, normal to these lines, we draw a new lines or the planes. It encloses the very small region, that smallest volume enclosed in this way, that smallest volume we call primitive unit cell, and in the reciprocal lattice is known as Wigner-Sage cell. Now, these are some distinguishing points between direct lattice and reciprocal lattice. Here, the animated GIF image for the geometric relationship between direct and reciprocal lattice is shown here. When X-rays are allowed to incident on the periodic array of the atom, they are diffracted and the image is shown in the form of array of lines on the screen. The resulting regular pattern of the light spot represent a reciprocal lattice. If the atoms are more widely spaced, the light spot gets closer and vice versa. If any other atoms is added, the intensity vary, but the periodicity position remains same. Such a pattern which determine the organization of atoms in the solid. Now we derive the relation between direct and reciprocal lattice vector. For deriving that relation, firstly we find the relation between normal to the plane and crystallographic axis ABC. For that purpose, we consider a primitive unit cell. That unit cell is represented by the three crystallographic axes A, B, and C. Such a primitive unit cell represented by height OR, which is at a distance equal to D100. We have to find what is the volume of the primitive unit cell. That volume we determine as we know what is the base area and what is the height of the unit cell. Therefore, we write one relation. As the height of unit cell is known, then volume of the unit cell is area of shaded base multiplied by height. That area of the shaded base we write in the vector form is B cross C, since that plane is perpendicular to the A axis. Using that relation, volume of the unit cell equal to area of shaded base and height, we simplified in that form area divided by volume. Take this volume on that side and separate one by height term. We get the next equation. We write this relation in the vector form. Since area we know B cross C and volume of the primitive unit cell A dot B cross C equal to 1 divided by height, we write in the vector form, where n is the unit vector normal to the plane BC along A star axis, and D100 is the interplanar spacing for 1 0 0 plane, since that plane is perpendicular to the A axis. Therefore, Miller plane is 1 0 0. That equation we write equation 1, where n we write earlier. That unit vector is normal to the base, is along the A star axis. We defined earlier the magnitude of the reciprocal lattice vector equal to m divided by d100, where m is the scale factor or magnification factor. That magnitude we write in terms of the vector. Vector A is equal to m times unit vector n divided by d100. That is the equation number 2. From equation 2, we write the equation 2 here. Equation 1 is known, is vector n divided by d100 equal to b cross c divided by a dot b cross c. That value we substituting here. And vector a star also written as a vector d star 100 equal to m multiplied by b cross c divided by a dot b cross c. In the same manner, if we choose another plane, that plane is perpendicular to the b axis, we draw normal to that plane. That normal along that b axis we call b star or d star 100. That equal to m times here the base area divided by volume of the unit cell is as it is in c cross a divided by a dot b cross c. Similarly, another plane, that plane is perpendicular to AB, means AB plane is perpendicular to C axis. We draw normal along that axis. That normal for AC AB plane, that we call C star. Therefore, we define the C star equal to or D star 001 equal to M times. This is the base area for AB plane. Therefore, A cross B divided by A dot B cross C. Where M, that scale factor or magnification factor, is unit in X-ray diffraction technique. Therefore, M is taken 1. Then this 3 equation becomes vector A star equal to B cross C divided by A dot B cross C, or B star, vector B star is equal to C cross A divided by A dot B cross C, and vector C star equal to A cross B divided by A dot B cross C. These 3 terms represent the reciprocal lattice vector, and these lattice vectors are expressed in terms of direct lattice vectors, and that gives the relation between reciprocal lattice vector and direct lattice vector. Here we explain, that is one of the figure we shown here, which gives the geometrical construction between direct unit cell and reciprocal unit cell. This is in the direct lattice. If we draw normal to the planes like BC plane, AC plane and AB plane, the vectors are A star, B star, C star, and it form another unit cell that we call reciprocal unit cell. Here we give some conditions about the reciprocal lattice vector which satisfy the relations. As vector A star is normal to vector B and C, that is vector A star dot B and vector A star dot C is always 0. Similarly, if the B star is normal to vector A and C, then it satisfies vector B star dot A and vector B star dot C is to be 0. And vector C star is normal to vector A and B. It also satisfies the same condition. Vector C star dot A and vector C star dot B becomes 0. But the vector A star dot A is always 1. Now we prove this. We substitute the reciprocal lattice vector and direct lattice vector. We take the dot product of the two vectors. Vector A star, we find a relation earlier. It is B cross C divided by A dot B cross C. Similarly, we also find another conditions. As we know, the reciprocal lattice vector B star dot vector B and vector C star dot vector C, that is equal to 1. See the one case. Vector A star dot A, vector A star, reciprocal lattice vector, we find a relation earlier. B cross C divided by A dot B cross C dot A is always 1, since numerator and denominator is same. Similarly, other condition also we get B star dot B is 1 and vector C star dot C is 1.